Hi everyone. So today we will be looking at the second engine of my savings of reaching 100k, my theoretical target. Okay, so in the previous video we have actually looked at arithmetic progression, okay, which in this model, okay, I start with an initial amount, and then every year I have some increment of sort, okay, and then I just ask myself how long does it take to reach 100k or whatever target that I want, discounting the fact that I will receive dividends or interest or anything. It's just pure nominal value of my money. So in this video today, we're going to look at another model which, okay, I invest the same amount yearly, but I do not increase my contribution over the years. I only stay with, for example, I start with 6,000 per year. I only invest 6,000 per year, but I receive a rate of returns of say 4%, but this 4% is theoretical and is the same every year, which is quite unlikely in the real sense, but it doesn't matter. In the real world, although I may not get 4% every year, but it is already a very good approximate, okay? As long as you're not using things like 10% or 20%, which is quite unlikely for any sound investment to give you that amount of returns. So how do I actually do that? I'm going to use what we call the geometric progression. So previously it's arithmetic, now it's geometric progression. Again, it's a very common question in the A-level H2 Maths syllabus to ask this kind of question. So let's start with this assumption. Okay, I want to get a $10,000 savings or investment value at the end of n years. I don't know how long is that, okay, but what I know is that with putting in 6,000 per year and getting my returns, I want to see when is my final value going to reach 100k. So I annually invest 6,000. My nominal growth rate is assumed at 4%. I target to get $100,000. So how many years will it take to reach the target? Okay, first of all, we understand the model first. Okay, so I start with 6,000 at the year number 1. I start, okay, with 6,000. At the end of the year, I will have 6,000 plus the interest or the returns of 4%. So I get 6,000 times 1.04. In year 2, I am going to start with this amount that I already have, and I add on another 6,000. At the end of the year, I will get this 6,000 with its interest. So we can see from here that we can see from the first line, okay, that we just multiply by this factor of 1.04 to see that I have both my capital plus my interest calculated into this product, right? So I multiply by 1.04, okay, and that simplifies to, I'm not going to press the number out, I'm just going to put it in mathematical notation, right? So in year 3, I would start with what I already have, which is 6,000, 1.04 square at 6,000, 1.04 at 6,000. This is the amount I'm going to start with. And then in the following year, as in the same year's end, I'm going to get 6,000, 1.04 square, 6,000, 1.04 plus 6,000, with the interest. N is capital. And that gives us 6,000, 1.043, 6,000, 1.042, 6,000, 1.04. So we just need to recognize the pattern. Year 1, power 1. Year 2 is 6,000 times 1.04 power 2, and then 1.04 power 1. Year 3, I will get 6,000 times 1.0 power 3, power 2, power 1. So if I were to generalize it to year end, right, I can skip the start. I straight away go to the end. I will start with a 6,000, 1.04, n. Because when it's year 3, I start with 3. It's year 2, I start with 2. So if year end, I will start with n, and I will get a decreasing number of the power n minus 1, n minus 2, all the way to 1.6,000 times 1.04 power 1. So this is what we call a geometric progression. So in a geometric progression, okay, I have a few things. I have my first term, in this sense is 6,000, okay, and then I have what we call the common ratio, which is, in this case, from one term to the next, I keep dividing by 1.04. If you look at it from this direction, so I keep on dividing by 1.04, but over here, if I start all the way from 1 upwards, I multiply by 1.04. So there's two different directions that I'm working with, right? So the common ratio in this question, it is 1 over 1.04. It doesn't matter, later I will explain in detail. So you can see that this is like the stacking system. In year 1, I start with 6,000 with the interest, and then the second year, okay, I stack again because I put in another amount of 6,000, but both years earned that interest of 1.0. My first 6,000 earned both years of interest. My second year only earned 1 year of interest, and it goes on. So when I try to read off this term, what it means is that this very first $6,000 that I've put in year number 1 has earned n number of years of interest. Okay, so the geometric progression, okay, in a more general sense starts as this. I have a first term a. To get the next term, I multiply r to it. To get the next term, I multiply r again, so I get ar squared, and then ar cubed, all the way to arn minus 1. So my first term is called a. My common ratio, okay, is r. Now, do not mistaken this. It's not the nominal growth rate. Okay, this is not interest rate or anything. Okay, why do I want to say this? Because, right, we have been using R as the rate of interest, rate of inflation, and things like that. I don't want you to confuse this R with the idea of common ratio. Okay, later you will see it. So what happens is that if I were to add GPs together, that means I want to consider A plus AR plus AR squared plus AR cubed all the way to ARN minus 1, right? Because I'm going to find my total portfolio value, correct? So same thing, I use the notation SN. But the way of doing this is not the same as what we did in GP, where I flip the whole thing over, right? Sorry, plus A. When I add them together, I don't always get a consistent term anymore. So whatever method that we have taught about in AP doesn't work here. But I can do a very similar method to do it, okay, not by adding but actually subtracting. But in order to subtract, I need to do something first. Okay, what do I need to do? Okay, let me write it down. AR plus AR square plus AR cube plus AR n minus 1 plus okay. So what I do is I multiply R to everybody, and what it will do is it shifts all the term by 1. Right? When I multiply by R, this term shifts here, this term shifts here, this term shifts here, and so on. This term shifts here because I multiply R to them. So what I can do is now I do a subtraction. So Rn minus Rsn, okay, all the terms in between gets cancelled, leaving us with the first minus of the last. And I can do a factorization. Followed by a division. So it can either look like that or it can look like that, depending on whether you like the minus 1 to be at the back or the front. Okay, up to you. So this is the summation. So the summation code tells me this: the total accumulated value of the annual contribution with all the years of interest, okay, is given by this formula here. So A is the first term, which is my first investment. The number of terms, which is number of years invested, and R is the common ratio. Again, don't mix it up with the rate of return. Okay, so when I assembly this into my equation here, right? Okay. Okay, so what happens is, just now we said the R is actually 1 over 1.04, but why is it now 1.04 instead? Okay, very simple. What we need to do is to do a reversal. Now I know I start from 1.04 power 1, 1.04 power 2, all the way to 6,000, 1.04 power n, and I'm done. Right? So I have n terms because I invested for n years. Okay, my 6,000 is my first term. My total value is 100,000. So my job now, okay, is to solve for n. But the issue is my n is in the exponent, right? So if I were to simplify everything that I want, right, I will get 1,000 after 100,000 is 6,000, 1.04 power n minus 1 divided by 0.04, right? So what will happen here, okay, is that I'm going to cancel this. Okay, 0.04 is actually 1 over 25. So it's 2,500 divided by 6 minus 1. Okay, after your simplification, okay, what will happen is it will be 100 over 6 times 1 over 20, oh sorry, 1 over 25. Okay, yeah, it's not 2500. Okay, I made a mistake. Okay, so this is 4, this is 2, this is 2 third. So 1.04 n equals to 5 third. Okay, so you will see that now I have a power n here, which I don't know how to solve, right? That's where natural log comes in. So natural log, or you can use ln, up to you. What you do is I use the law of indices. I will get ln 1.04 power n equals to ln 5 third, and ln 1.04 equals to ln 5 third. So n equals to ln 5 third over ln 1.04. So this value works out to be approximately 13. So what it means is that it will take me 13 years to invest 6,000 yearly with a growth rate of 4%, okay, to meet 100k invested in value, total invested. Okay, so now I have a very objective way of looking at things. If I invest consistently for 13 years with a good growth rate, 6,000 a year, I will end up with 100k in 13 years. So what if my target isn't 100k, or what if my growth rate is actually higher? You actually found something that gives you better rate, right? So I can also, same as the AP, okay, come up with something that helps me to generalize this formula, right? So my Sn becomes T, my R power n, remember, this is actually your common ratio, not the 7% that we're talking about, okay, and I put it into the equation, okay, and then same thing, I multiply the R minus 1 over and divide, I get this equation, okay. So from here I just need to add 1 on both sides and do a common LCM. So what will happen is I get R power n equals to A plus T times R minus 1 divided by A. So in order to solve for n here, I am going to take the logarithms again. So how do I actually do the logarithms here? Very simple. R power n equals to A plus T R minus 1 divided by A, and ln R equals to A plus T R minus 1. Okay, so we know ln A over B equals to ln A minus ln B, right? That's our rule for logarithms. So I have ln A plus T R minus 1 minus ln A divided by ln R equals to n. Okay, so this is your universal timeline formula, where n is your number of years to get to your target. Okay, the starting annual investment amount that is kept constant every year is A. Your target amount is this T, your ultimate financial goal, and your vehicle R here. Please remember, this R is the common ratio, okay, which is 1 plus the growth rate that you are looking at. Okay, so R equals to 1 plus growth rate. So in theory versus reality, the math models are discrete and predictable. Okay, it is an annual amount that jumps because you put in things at the start of the year or end of the year, up to you. Okay, the growth happens exactly once a year, but it may not happen so in a volatile market or in a usual market where it goes up and down over the years. Okay, it's perfectly stable for our case of 4%, which is not in the usual that case. The real world is actually continuous and volatile. Okay, and the incremental investment happens monthly, daily, yearly, up to you to choose. Okay, the growth and your investment amount happens simultaneously, because as much as you are putting in annual contribution with increment, the rate of interest earned per year keeps changing. That is what we're going to look at in reality, what progression actually models it in the next video. So you definitely have to come back again to know what's the real deal. Okay, so the final point that I want to make is, okay, these two models up till now tell us the clarity of time. Okay, it can help you to make good financial planning. You know how much you can afford to put in monthly, and then how much you can increase yearly. It tells you whether it's a possible goal or impossible goal. The clarity of value also tells us how we can also know exactly how long it takes for my total portfolio to compound to that value that I want. Okay, of course, the human element is that the math is flawless, but in order to achieve our goals, we must stay invested and stay disciplined to do that kind of yearly increment, yearly investment in a very disciplined way. Okay, so thanks for watching. We have come to the end of today's video. If you like my video, please share, like, comment, and subscribe to my channel. If you have any maths problems that you would like me to explain, or any daily life problem that you think maths can help you, please send me a message and I will see whether I can make a video for it. Thank you.